Today is 4-4, choosing a simple random sample. So, like, here's like a little scenario here of how to do a nice little random sample. Look how cool this chick is here. Each day in class, Miss Herbert randomly selects 5 students to present homework problems on a whiteboard. To make this selection, like, she uses a set of craft sticks with each student name written on the stick. She puts the sticks in her cowboy hat, mixes them well, and pulls out 5 sticks. Like, how awesome is that? That they just didn't even say a hat. It had to be a cowboy hat. So the students' names that are on the 5 sticks are selected and present the homework problems. That's just a simple random sample. Put all your names in a hat and, like, pull them out. Everybody's, like, name was on an equal size stick. That's one way to do a simple random sample. So to define the things right here for our worksheet, a simple random sample, they usually call it SRS. You're going to see that abbreviated a lot, like simple random sample, is a sample chosen in such a way that every group of N individuals, N is just like the number of people in the population, so every group of N individuals has an equal chance to be selected in that sample. So that's a simple random sample, and then we might as well define sampling variability since we're right here, is the fact that different random samples of the same size from the same population, produce different estimates. So there'll be some variability in the samples. That's called sampling variability, and we'll see that when we dive into some questions today. It's a pretty basic day until we get to the end. And then it's just like kind of head scratching. It's like, say, what now? You know, like honestly, I think some of it feels a little backwards the first couple times you learn it, and then the more you do it, the more it starts making sense. So, all right, so check it out. There's a couple of ways to do it. So here's what we got on the first one. When landfills run out of room, they are sometimes converted into parks. Does the presence of a landfill underneath affect the trees that grow in the park? So one such park has 283 trees, and researchers want to closely inspect a sample of just 20 trees. Describe how to select a simple random sample of 20 trees using slips of paper. So, all right, this is pretty lame to do it slips of paper-wise in the world that we live in, but you can do it, and your homework asks a lot of it. Give each tree a distinct label from 1 to 283. Right? Aren't there 283 trees total, right? So you're just going to number all the trees, you know, like 1 to 283. Number 283 identically sized slips of paper, right, from 1 to 283. So every slip of paper is identical. You put them into a hat and mix well. And then since you're only testing for 20 trees, you're going to select 20 slips of paper and inspect the 20 trees that are numbered. Doesn't that sound tedious, though, to do that? Like, if you wanted to, like, totally pick 20 random trees out there using slips of paper, you'd have to get 283 slips equally the same. What a waste of time. Another way to do it is with a random number generator. You've even seen me use some random number generators in here. The computer does it all. So what you do is, if you use a random number generator, you give each tree a distinct label from 1 to 283, like you're still labeling all the trees. Randomly generate 20 integers from 1 to 283, but the problem with random number generators is it will have repeats, like it'll repeat sometimes, so then inspect the 20 trees. So let me show you that. That's how simple it is with this random number generator. I just have to number all my trees. You'd go and do that, and then I'd have 1 to 283, and then I'd do that 20 times. All right, tree 142, we're going to expect you. Tree 79, tree 225, and etc., right? You know, like you would totally just do that. If you get any repeat guys, you just ignore it and try again in that situation. But wouldn't that be so much faster than making all those slips of paper in that case? So slips of paper is kind of silly. It's easy for small things. Like if we want to do that with us, you know, we're a small group, it would make sense. So, all right. Question 2. A safety engineer at an automobile assembly plant knows that 180 pickup trucks will be assembled tomorrow. To meet federal regulations, the engineer must select 5 of those vehicles for safety testing. I will let you and a neighbor try to fill out these blanks. You know, there's 180 total pickup trucks, and they want to select 5 of them. Using slips of paper, give this guy a shot. I'm going to pause the video here real quick. So let's see how we did. Give each truck a distinct label from 1 to 180, right? Isn't that the total number of trucks in that case? Number 180, identically slips of paper from 1 to 180. Put these papers in a hat and mix well, and how many should we select? Select how many slips of paper? 5 slips of paper, and test the 5 trucks. It's pretty basic. You've been doing things like this for years in classrooms where they randomly select students by putting names in hats, and sometimes they have the wheel where they spin the wheel with your name on it, you know, and all that stuff. So pretty neat. So, all right. What if we wanted to do it with a random number generator? Give each truck a distinct label from what to what? 1 to 180, right? There's 180. Randomly generate 5 integers from 1 to 180. Ignoring repeated integers. Test the 5 trucks that are labeled with the generated integers to see if they meet federal regulations. So that's a nice random sample in that case, taking all the bias out of it. You feel okay with those 2 examples about random samples? So, all right. And then there's sampling variability. You remember a couple of days ago we read those words from the Federalist Papers, and like we picked like 5 words at random or whatever, and or it wasn't even at random. You just picked 5 words. When you did it by yourself, a lot of people had some bias in what they picked because it's like, oh, I picked nothing but big words, or I picked nothing but small words kind of stuff. You didn't randomly do it. And then here, when they did it randomly by picking words, the dots were much closer together. If we keep doing that over and over and over again, this sample would not always look the same. There would be some variability. So there is some variability with sampling variability. We defined it earlier, and what it is just like if you keep taking random samples of the same size from the same population, you're going to get different estimates. So here we go. Here's our first example of sampling variability. The median household income of a random sample of 371 Virginia households is 68 grand plus. Do you think that the median income of all Virginia households is equal to that? Like, should this number right here be the exact true median? What do you think, yes or no? They randomly sampled 371 households in Virginia. Is that an accurate enough thing to say? Yes, sir, Bob, that is the true median of all Virginia households. Yes or no? No way. It is not. Because different random samples will produce different medians. Like if you did that again with 371 different households, you would get a different answer most likely. You know what I mean? It would be close, but it would be different. It is unlikely that this sample provides a median that is exactly correct. So that sample had 371 households in it. What do you think would happen if they increased the sample to 1,000 households, which is more, right? You know, it's like 3 times as much in that situation. Do you think the estimate should be more or less likely to be close to the true median? What do you think, more or less likely? The more people you sample, what do you think, the more accurate or the less accurate? It would be more accurate to the median income, the true median. Like you would have to sample everybody. You would have to ask every single household in Virginia to get the true median. But there's no way that that's like humanly possible. You know, it's just like way too hard to do. So the more people they ask, the more likely it is. So, and then let's fill out this chart. Using a larger sample reduces the sampling variability. So the more people you ask, the less it's going to vary. In other words, the estimates become closer to the truth. But be careful, increasing sample size does not reduce the bias. Like if we go back to those push-up questions that we did from lesson 4.2, if I said, hey, come on down and sign up for the push-up contest, even if you got more volunteers, it doesn't mean that the bias has gone away because the people who are good at push-ups would just probably show up. Like there'd just be more of them. Or, hey, do you wash your hands after using a public restroom? Even if you asked more people, it doesn't stop them from lying about it, you know? So it doesn't reduce the bias. So, cool. That's, I think, pretty basic. I think we get that. Now, for the weird part, the inference. And the applets are going to help us. You don't need to get yours out today because I'm just going to do the applets for you, but you need to kind of pay attention to how I do it. So check it out. Do students prefer name brand cookies? I almost bought some cookies, but I kind of forgot about it. 30 randomly selected high school students were asked to taste 2 unlabeled cookies and identify which cookie they preferred. One of these cookies was name brand, Chip Ahoy's, right? The other was just a store brand, just to kind of call it, basically, it's like your Kroger brand, you know, of cookies or anything like that, just plain Jane Dillon. In this case, it was called Chipmates, but it was just a generic. The order in which the 2 cookies were presented to the student was using a coin flip, so it was random. And of these 30 students, 19 preferred the name brand cookie and 11 preferred the store brand cookie. Would you agree that more than half liked the name brand, you know? More than half. There's 30 students, more than half. But what they asked, the statisticians say, is that a true representation or is it just kind of coincidence in that case? Because you only surveyed 30 people, right? So they said, let's do this. Let's use technology to see if that would be a good thing, like if students really do prefer the name brand or if that was just by chance. So just basic statistics. How do you feel about there are 2 cookies, right? And if it was an equal shot, right, that they didn't care which one, wouldn't there be a 50-50 shot, you know, since there's 2 cookies? If it was like taste didn't mean anything, there was a 50-50 shot. Well, check out this simulation that I could do. I want to show you how to do it on the applet. Again, if you need help doing this with homework, I will help you. But you select the one categorical variable, single group, and we go put our 2 guys in. So let's just call this name brand cookie, and then the other one is the store brand. And would you believe 19 students selected the name brand and 11 students selected the store brand, right? That's what happened in that experiment. So I'm going to begin some analysis. We've done this before. They made a bar chart for us. Ooh, a bar chart. But now we can scroll down and start using some of this things called inference, right? So inference is where we're going to do the survey like many times. We're going to infer what happened using technology. So I want to simulate a sample count and indicate that I want to see how many kids are going to choose the name brand. That's what we're interested in. In this one little survey, 63% of the kids chose the name brand. So the hypothesized percent is 50%, because that's what would happen if it was equal. And I want to add 100 different samples. So let's see if this works. Sometimes this 50 works. Sometimes you got to change it to 0.5. Let's see what it did. It did it for me, right? There it is. It did the sample 100 different times to where it asked for 30 people to be surveyed. What do you choose? And they did it at 50%, like would choose this and 50% that. They just kind of randomly did it, like if they flipped a coin kind of thing. So here's what we want to know. We want to know if that number 19, so if I change this to greater than or equal to 19, and if I click this count button right here, it's going to count how many students, like how many times 19 or more students did it for me. So would you believe, on my example right here, it says right here, there are 9 times where that happened in that case. And the beauty of doing it 100 times is, well, however many dots it is, that's the percent that you got, you know, because it's like 9 out of 100 in that case. That's 9%. So let's go back and answer some questions here on this guy. So I did this. Right here it says, explain how the graph illustrates the concept of sampling variability. So these will be like your little drop downs on your homework. If researchers take many random sample size of size 30, because that's what I did. I did a sample size of size 30. There was 19 and 11, right? Size 30 in that case. From a population who showed no preference for cookie takes. That's why I did it 50%. The number of students in the sample will vary from about blank to blank. Here's what you got to do. You got to go on your applet and look at your low number. Our low number is 9. If you look way over here, 9, and the big number is 23, so 9 to 23. Not everybody's is going to do the same thing. You know, like if you ran this applet, your lowest might not be 9 and your highest might not be 23. It might be just a little bit different in that situation. So that's the whole concept of variability. Because it was randomized, your survey results could be different than mine, it could be different than somebody else's. In the simulation, what percent of samples resulted in 19 or more students preferring cookies? That's right here. That's this 9%. 9% did that. So 9% of the time, Students, like 19 or more students preferred the name brand cookie. So let's see what this says. In the actual study, 19 students preferred the name brand. Based on results of Part B, is there convincing evidence that students like these have a preference for the name brand cookie? First, before we fill this thing out, what's your gut feeling? Because this is where I got confused myself, and I'm the dude with the math degree. 9% of the time, 19 or more students preferred the name brand cookie. Would you say that that is likely to happen or unlikely to happen? Your gut feeling. Good for you. You know, I didn't think that was very likely to happen. I thought that was unlikely. But you are correct. It is likely to happen. Here's how I did it. Did it even happen when they did the random survey? What do you think? Did it even happen? Did it ever happen to where 19 or more students said they prefer the name brand cookie? Did it happen? You bet your butt it did. It happened 9 different times, right? It totally happened. So because the result of 19 or more successes is somewhat likely. Somewhat likely. It did happen, right? You know, it wasn't impossible. Mr. Powell's class decided that there is not convincing evidence. That to me seems backwards, but that's what the book says we got to go with, that there is not convincing evidence that students at the high school preferred the name brand cookies. Kind of weird. I think it's easier to understand if we try one more. The last example of the day, baby. It's a lot of reading, but still. Here's what they did, another experiment with candy. Researchers at the University of Michigan designed a study to find out this. The researchers gave 22 students 5 different Hershey's Kisses. You know what a Hershey's Kiss is, right? The little teardrop chocolate thing, you know? But the 5 different ones, there was milk chocolate, there was dark chocolate, there was creme, there was caramel, and there was almond. So 5 different varieties in a random order. It's like, here you go, here's one, eat it. Here's another one, eat it. Here's another one, eat it, in a random order. And students were asked to rate each one. But here's the goofy part. They were not told how many they were going to get. Right? They were just like, hey, I want you to rate these. You know, here's what you get. I'm going to give you a Hershey's Kiss. They're all going to be different. I want you to rate them by which one you like. But they weren't told how many they were going to taste. However, when the 5th and final kiss was presented, they were informed, hey, this is your last one. This is the last one. Every time when they gave them the 5th one, they said, this is your last one. They said out of all 22 of those students, 14 of them gave that final kiss the highest rating. The final one. When they were told, this is the last one, 14 out of 22, 64%, gave that final kiss the highest rating. So here's what they want to know. If you did it even, there's a 1 out of 5 shot that you choose that last one to be the one you like the most, which is 20%. That's if it was even. 20%. 64% is way freaking higher than 20%. So they wanted to know if this data provides convincing evidence that more than 20% of students like these prefer the last kiss they taste using the applet to run 100 simple random samples. So I got the applet set up for it. Here's what I set it up as. I set it up like so. Let me get this out of the way. That if you chose the last kiss, 14 out of those 22 chose the last Hershey's Kiss as their guy. That means that 8 somehow chose one of the first 4 kisses, right? There's only 2 situations. Did you choose the last one or not in that case? So I'll begin the analysis. And to run inference on it, I got to scroll on down. There we go. There's the scroll on down. Hypothesized percent is 20% because that's what it would be fair, and if I ran 100 surveys, 100 different times. I'm going to add that up, and here's what happened. Count the number of dots that are greater than or equal to 14. Count. How many times did 14 people ever say they were going to choose the last kiss? If it was fair, if it was random, how many times did that ever happen? Never. Right? That never happened. If they treated each Hershey's Kiss fairly, like it has a 20% chance of showing up, and you only asked 22 people, right? In 100 different tries, no one ever said that happened. I'm going to do it bigger. You told me earlier that if I had more than 100, it gets more accurate, so I'm going to add samples. There's 200. There's still nobody. Let's zoom out a little bit so we can see this. If I add samples again, there's still nobody, still nobody, still nobody, still nobody, still nobody. I got it up to 700 different tries. It still never, ever, ever, ever happened. So let's go back and answer these questions. Explain how your graph illustrates sampling variability. If the researchers take random samples of size 22, that's how many kids were asked originally, from a population of students who show no preference on what it tastes like. That means that's the 20%. No preference. The preferred kiss varied from about, crap, I forgot to look at it. You just go with your low and your high, so I'm going to make things up. Let's just go 4 to 10. You know, I don't remember what the boundaries were, but on that very first one, we should have looked up the boundaries. There was 4 to 10. Those were our boundaries. That's how much it varied. Based on the simulation, what percent of students resulted in 14 or more students preferring the last kiss? 0%. 0% of them did that. And in the actual study, 14 students preferred the last kiss based on your example. Is there convincing evidence? What do you think? Yes or no? Is there convincing evidence to say that students prefer the last thing that they taste? It's kind of backwards of what you think, because it is, you know, unlikely to get 14 or more students to prefer the last kiss by chance. There is convincing evidence that students like these prefer the last thing they taste. So the experiment was kind of backwards. It's just like, okay, there's no way that you are just like being random with it. The last thing you tasted is what you're going to prefer. So I think thinking backwards on this last part of the question makes the most sense to me. It's like, okay, this is what I'm thinking, and it's going to be the backwards of that. So let's give it a shot on the homework.